In our previous video, we were looking at image recognition of the MNIST dataset. So these are handwritten numbers. And could we build an algorithm that would identify these different numbers? So we have from sklearn.datasets imported using fetch openml. And then we use that fetch openml to call the MNIST _784 dataset version 1, labeling it MNIST. We have then pulled X, which is the data, and Y, which it calls the target, which is going to be our labels. So once we've pulled that information, we can, as we did in the previous video, we can do image recognition. In this particular video, what we want to do is we want to look at how do you denoise an image. So I'm just going to scroll down here. So we can use those same k-nearest neighbors method to actually get rid of noise to help enhance an image. So think about, for example, if you're in Photoshop and you want to make the image clearer, how is it doing that? Well, it's actually a classification model using k-nearest neighbors to help identify what is noise and what is not, so that we can clean up the image, enhance, denoise the image. If you want to work alongside with us, we are here at drstephpowers.github.io/BIA. And here we are in this section where we're looking at k-nearest neighbors use cases. All right, so let's go back to our data set here. So what we're going to do is we're going to take that MNIST data set and we are going to add a bunch of noise to it. Okay, we're going to make it a bit more blurry. So how do we do that? We're going to import numpy.random and we're going to call it NR for short. Okay, so this allows us to randomly generate some numbers and we're going to call this noise. So noise is equal to an NR. We're going to use that numpy random and we're going to randomly generate some integers, whole numbers. And we're going to randomly generate integers between 0 and 100. And we're going to do this for the length of our training data and our testing data. So the length of the training data, which in the previous scenario, what did we end up doing? We use the first 60,000 to be our training data. So 60,000 images are going to be the training data. So we're going to randomly generate numbers between 0 and 100 for those 60,000 different images. And because we're going to randomly generate data for every pixel, we actually have 784 variables, right, for each of those images. So what we're going to do when we randomly generate is we're going to randomly generate integers for all 60,000 pictures, but also for all 784 variables. That's what this is here in this parentheses, is that says we're going to do it for both the variables and for all the different images. So we're going to randomly generate some noise, and then we're going to add that noise to the data itself. Okay, we are going to add it to the training data, and we're going to add it to the testing data. So we're going to repeat this twice. First, we're going to create noise using our random integer between 0 and 100, so whole numbers, for the whole data set, all variables, all images, for the training data. And then we're going to repeat that and do the same thing, randomly generating noise for the test data. Okay, so that's why it's twice. Once for the training, once for the testing. To see what this looks like, let's take our X train, and we now have an N here because this is now noisy X train. And let's look at index location 2. Okay, let's call that example 3. So what we have here is you can now see there is a bunch of noise, because when we looked at a bunch of these examples previously, there were a lot of zeros, and there's not a lot of zeros anymore. Okay, to visualize this, we're going to use our numpy, reshape, and ravel to turn it into 28 by 28 so that we can actually look at the image. So make sure you are importing numpy as NP. We're also going to need to import matplotlib.pyplot as PLT so that we can create our graph here, which is going to show our picture. So we'll do plt.imshow, take our example 3 image that we have reshaped. We're going to make it a color map that is binary because it's just shades of gray. So now we can see here's letter 4 that we saw before, but it has a lot of noise. Okay. So what we want to do is we want to actually start here with this noisy image and see if we can create a classification model that removes the noise. Okay. So sharpen, enhance, remove all that noise and distraction from this. So how do we do that? Well, we use the K nearest neighbors. And we have it set right now at 3 nearest neighbors. Our data set can handle that. Again, if you want to catch you want your classifications to catch all the different variety and little changes, then smaller. If it can look at a bigger group and make a decision there, so we can be more general, we can have the differences are quite big and distinct, then we can go with a larger number of neighbors. Here we'll make it on the lower side. Remember, it has to be odd. Let's call our K neighbors classifier. And so make sure you have imported that. We actually imported it. Ugh, getting into such bad behavior. We imported it back when we did the previous video. So make sure that you have imported that. Where did I go? So this is the sklearn.neighbors, import kneighbors classifier, and from sklearn.metrics, import the accuracy score. So we should have put that at the top as good practice. All right, so let's go. Call the classifier method, fit the method on our xtrain_n, so this is on the noisy data. Now notice here, we're not doing train and test. What we're gonna do is we're going to train it on the noisy version, and the label here is going to be the non-noisy version. So what we're doing is we're saying, okay, this is the noisy version of 4, and this is the non-noisy version of 4, so that it can learn what a noisy version and a non-noisy version look like as it tries to classify. So then we run this and we do the predictor. It's not going to be predicting a single label. It's actually going to predict a string of values for all 784 pixels. So we do y_predict, KNN.predict, and then what we're going to do is we're going to test it on the noisy data. And what it outputs here is it outputs values for all 784 variables. For each of those test ones. So we'll have it create that. So we can see running that prediction took a good 7 minutes and 20 seconds. It takes a lot longer to run this particular type of model than the label because we're trying to predict 784 variable values. And remember for those that each of those can be numbers between essentially, 255. So that's a lot of labels. And that's labels for 784 variables. So it takes much longer to run this particular algorithm. All right, so we have predicted those different pixel numbers for those 784 variables for the, 10,000 test images. So let's see how well this works. We're going to create example 4, and example 4 is going to be the noisy data, and we'll do index location 100, and then we're going to reshape that test data, use reshape, use ravel, turn into the 28 by 28, and then use our matplotlib.pyplot as PLT, and let's create the image. So this is the same code we've been using before. Let's create for index location 100 from the noisy test data. Let's see what that image creates. That image creates this noisy 6. Okay. Now we're going to take our predicted, so same location, so y predicted 100. And we're going to do y predicted 100. We're going to take those pixels. We're going to reshape that using our reshape ravel to be 28 by 28. And let's then plot this. So here's what it predicts is a noise reduced image. So you can see here, it loses some of it where it's not quite able to distinguish between the noise and the image, but we can see that a lot of it is cleaned up with our classification. You can choose, pick a different number. That was 100. Let's do 1000. Repeat our process here. Here's our noisy weird shape 9. See how it did. And how well did it denoise that image? Oh, sorry. You got to change it here too. All right, so we take our predicted, we got to take it here. Otherwise, we're still at that same image as before. There we go. There is our denoised number 9. So you can see how well it's doing in terms of removing the noise from the image. And so this is just a very basic model, but this is the same thing that we see when we are looking at programs like Photoshop, where we are trying to enhance the image. And in fact, these models are very simple, but we could do neural network versions of these models where we're looking for hidden layers and greater relationships, more complicated machine learning algorithms to further enhance the images. And that's what we're seeing today as we look at some of the software that is available. Whether it's video games, being able to generate and change things on the fly, whether we're talking about Photoshop being able to enhance images, whether we're talking about being able to watch old TV shows that have been up-resed. These are all coming from classification models.